Hello and a warm welcome back. Today on the bench is a load of various components which hopefully I'll make a valve tester, a simple valve tester out of. The weather, I don't know if you can hear, is reset back to rain. We're into May, Beltaner's gone and we should be having lots of lovely sunshine, but yeah, we've got bloody rain, so here we are. Messing about with electronics. So what have we got? We have a big mains transformer which has various windings on it. I rewound this a little while back, so we've got a couple of high voltage windings of 240 volts AC, 260 volts AC, 40 volts AC, and what else we got? 40 volts and 22 volts I think. So basically that should supply the high voltage for a screen supply, a high voltage winding for an anode supply, a bias winding, that's the 40 volts, and a variable DC voltage for supplying heaters. Essentially all you need to test a valve within limits is a few high voltage supplies, and then you just measure the current going through the valve, and there you go. You obviously test it at certain test conditions and then compare that to the valve's data sheet, and if it is lower than specified then potentially it's a duff valve. If it's a little bit higher, all well and good. So I built Mark 1 of this version years and years ago when I didn't know so much as I know now. I still know bugger all, but I know a little bit more than what I did then. And so over the years I've tried various variable high voltage supplies using, this is a MOSFET. That's a very pretty simple MOSFET follower, source follower sort of type circuit. We've got this one here which is a little bit more complex, but I found didn't work as well. Again, this is another MOSFET source follower, again a little bit more complex than that one, and so on and so forth. However, the thing that I found when testing valves, especially ones, testing valves that are unknown and probably haven't had any power applied to them since they were made, is that if they're a little bit gassy, then what happens is the anode current goes full bore, and then what happens is that with a MOSFET source follower type supply, it blows a MOSFET. These are IRF 830s in there, and I've got some sort of more substantial MOSFETs in there, but basically all MOSFETs within reason are designed for switching off, on, off, on, off, on. They're not made for linear operation. And so what I found is that it just blows a MOSFET, and I'm fed up of changing fecking MOSFETs. So while a sort of MOSFET source follower power supply, variable power supply, may do for the screen, I'm thinking of going and doing something a little bit different, and that is to use a variable high voltage supply that uses valves. Valves are a little bit more forgiving as regards high voltage transients and things of that nature. So yeah, I'm gonna have a look at building a variable valve power supply. It needs to supply about 300 to 400 volts at I mean, most valves are very low current, so at the most probably 100 milliamps, but with the provision possibly to supply a little bit more. And so somebody recently sent me these 12E14 valves. I've no idea whether they're any good or not, that's why we need a valve tester. And they are specifically designed for high voltage power supplies. And then these are just a few sort of various triodes and pentodes that we can use to control the big series pass valves. This was Mark 1 version, and as you can see I've got various analog moving coil meters and various pots and whatnot. I was using this patch board here. So all these is pins 1 to 9, because most of the valves are either 9 pin, 7 pin, 8 pin. I'm not after like trying to test compactrons and all that with 12 or more pins. So 1 to 9 pins, and then basically so that's our anode supply. You can just go boof to pin 6 or whatever. That was my heater supply and all the rest of it. However, amongst all the junk that I've got, it's not junk, I mean these are really tasty, very well built big switches. So I've got these big switches that can more than handle the current, and I'm thinking of using one of those, or instead of the patch, what the fuck is it called? Patch bay. Instead of using the patch bay. This is another one here, and this is another one, although this will need all those disconnecting and unsoldering to be able to probably do the job, but we'll have a look. But first I need to build, or just prototype, the high voltage anode supply using valves. And one thing I should finally mention before I get stuck in is that a friend on a forum that I'm on has recently designed and had these PCBs made up, and basically that allows anybody to test the GM of a valve and a few other little bits and bobs. More on that later. I've also got these other PCBs that somebody kindly sent me. It's just basically a simple power supply PCB. Whether I'll use it or not, I don't know. And this one is I think that's a heater power supply, and this one is a Valve Wizard power supply PCB. That's a little bit more involved in that it can supply most of the sort of voltages for a valve guitar amplifier, so it's not really what we need here. First though, I want to dismantle all this gubbins on here, because I'm not going to be using this again, so that I can reuse all the sockets. And there are a lot of precision potentiometers, 10-turn potentiometers on here as well, switches, meters and all the rest of it. So let's get all that off and then we can start afresh. Well, there's all the bits off the front panel, or most of the bits off the front panel. A lot of these are the 4mm banana jacks that were on this patch panel. And as I was taking these off, I don't know quite why I started taking them off, I just sort of got stuck into the job. And then I thought, well, you've got to have essentially where are we? Cathode just goes to ground, so we've got to switch the anode, the bias and the screen grid voltages, which means 3 switches, which can all be replaced by this one patch panel. I have only one big switch that is suitable for the job. This is a 11-way, let me just have a look, 1 pole 11-way. So that's the only one that will do. The other ones, where the hell are they gone? The other ones, this one here is 2 stacks of 1 pole, is that right on, 1 pole 3-way. So that's 3 times 1 pole 3-way, which I could maybe get to work by switching, say using 2 switches. No, you can't bloody see. So by using, oh, let's get this fucking thing sorted out. I could maybe finagle that, so using one of the switches to then switch on to the next switch sort of thing, but that's just a waste of a switch, I think. And then this one is a 2 pole, 1 2 3 4 2 pole 6-way, so that one might serve. Maybe I could finagle that one to a 1 pole 9-way switch. Switch terminology is a bit of a mind bender, but really I think I'm just better sticking with the patch bay. So we've got loads of switches, sockets and all the rest of it. We just got to rebuild it back into a valve tester. Well, sunny day today. Instead of frolicking in the countryside, I'm indoors messing about with high voltage, which is a very healthy pursuit in my mind. This is just a prototype knocked up high voltage variable power supply using a 12E14 and a Russian ECC83. I think it's a 6N2PEV. At the moment I've just been experimenting with, this is a Zener dropper sort of thing that's feeding the screen at the moment, but for the sake of, where do you call it, demonstration, I'll just connect it to the anode. So it's basically triode strapped. That's the 12E14 is triode strapped. So this is the voltage reading across these 2 big power resistors. This is a 2K and this is an 820R, so we've got about 3K resistance as the load. Let's power it up. That's the heater. I'm using my big high voltage power supply to test this. .200 volts going in. .300 volts. .350 volts, which is about what we would have going in if we use this mains transformer here. Hopefully you can see everything at the same time. So we've got this potentiometer here that should adjust the voltage. So as you can see, we've got what, about 280 volts, 350 going in, so we're dropping 70 volts across the series pass valve, which is not good. And I have an adjustment of about 150 volts to 280 volts. Earlier on I tested it with just the 2K power resistor, and with a voltage of, what was it, 230 volts, 2K load, that equates to 100 milliamps current, high voltage current. Having tried the 12E14 out, they do they do the job. They're rated at 35 watts, more than adequate for most valve testing. I'm going to try a 6080. I'm going to try swapping to a 6080 because when I built that adjustable power supply in the big Class A 807 amplifier, I found that a 6080 had less voltage drop across it. So I'm going to rewire the socket there for a 6080 and then we'll do some more testing. So I'll swap the 12E14 for a parallel wired 6080 triode, and as you can see we have got a, I hope you can bloody see, the screen is crap on these cameras. Yeah, looks like you can see we've got 323 volts, so it is dropping less voltage. What were it last time? 386, was that right? 286. We're getting an extra, let's say 30 volts. Let's call that 30 volts, and we can go down to 170 volts. So we need to do some adjustment. I'd like to be able to get, I don't need to go down to 0, and that would be really pushing the valve a hell of a lot. I'd be pushing any series pass device a lot to drop the full voltage across, you know, the full, what was it, 360 volts across. Like any device, you're going to be pushing it. So we need to adjust things. Let me turn this off because that way no mistakes are going to get made. Right, that's a bit safer now. The circuit was thrown together and the Zener that I used wasn't the specified 75 volt Zener, it was an 80 volt Zener. Let's have a look at the schematic. Where's all my pointy things gone? Right, here's a schematic, I hope you can make it out. This is our ECC83, let's call it 12AX7. One end is configured as one of the triodes, should I say, is configured as a cathode follower. Its grid is set by this Zener here. Although it says 75 volts, I've actually got an 82 volt Zener in there. So the grid is set. We can't go any lower than that voltage. And then basically, because that's tied more or less like a long-tail pair, like a differential pair, the other grid moves in relation to this grid, and that is set by this pot here. That should be fine, that Zener should be fine. What we need to actually do here is reconfigure this potential divider here. So we've got a potential divider formed by this 47k, 12k, and although it says 25k here, I've got a 50k. Let's have a play with this voltage divider and see if we can get down to 150 volts. Now I've got the anode power supply, variable power supply, more or less sorted out. We'll try and have a look at the general sort of layout of a valve tester. This is just a simple valve tester, and there's things not on here that might be added later. So this is just a very basic valve tester. So you've got essentially two high voltage power supplies. One here shown in red, and that's to supply the anode. The cathode of the valve under test is basically just tied to ground. So we've got that high voltage power supply there. In the past I've made them from 0 to say 350 volts ish up to about 100 milliamps, but that's not really necessary. for most valves, you know, a valve is a high voltage, low current device for the most part. So about 100 milliamps is about right, but we only need to really supply it from about 150 to say 350 volts, something like that, in that rough ballpark. I'll get into my method of testing things later, how to test it and what to set the valve tester to. We'll get into that later. And then, because we are testing pentodes and beam tetrodes, we also need a second high voltage power supply here, shown in purple. And this one, I won't make that a valve regulated power supply. I'll use a circuit similar to this. I hope you can see that. So it's basically a very simple MOSFET follower. Here's our main power sort of MOSFET here. We've got a, obviously, like a DC, simple DC power supply, bridge rectifier, big capacitor, nothing fancy, maybe a CLC filter, but we can just use loads of capacitance really, something like, you know, 220 microfarads to filter the actual supply. Ripple isn't a really, you know, ripple isn't a big issue here, but with 220 microfarads of capacitance, that should stomp on any ripple, as long as the transformer can supply it, that is. And so you've got ground here, we've got a pot here. It's usually something like a 470k pot, another 470k stopper resistor going to the, that should go to the grid, not the grid, is it the grid? It's not the grid, is it? It's the gate, isn't it, on a MOSFET? Sorry, I'm still in valve mode. We've got a couple of protection Zeners there, back to back, 15 volt Zeners. As I said, this is MOSFET follower. We've got another protection diode here, reverse biased across the drain and source. Small drop-in resistor here, and then we've just got this MPSA 42, like that, 100 ohm resistor on its emitter. Sorry, trying not to really think about the correct vernacular. So something simple like that, and that should supply the grid, the screen, because the screen is usually on most valves at about 1/10 of the anode current. So that's the two high voltage power supplies sorted. Next we need a lower voltage power supply to supply the heater or heaters of the valve in question. And so something like 0 to about 30 volts, capable of about 3 amps, should be sufficient. And lastly, the most important of them all is, and that one is obviously shown in black there for the heater, and in day glow orange is our bias supply. And again, that needs to be at about 0 to 30-40 volts, something like that. Doesn't need to have a massive current capability, and again that is connected to the control grid of the device on the test. And lastly, we've got this here, and this is, I'm going to try and build this circuit, which is a friend has designed this. Essentially, on this side here we've got a lot of resistors that just drop down the voltage, going into a load of op amps. And as far as I remember reading the thing, I'm not a big one up for reading on things and retaining information. It's a I can't remember. It's a measurement unit, so we should be able to measure the GM. I can't remember about all the specifics, we'll get into that. Basically there's a TL071 and a load of TL072s. blah 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 on there. We'll get into the specifics of that later, but you don't need that really to test a valve. For years I've tested valves just on the emission only. And the other thing I haven't shown, sorry, waffling on a bit, look to remember, are all the measurement devices. So we obviously need to know what voltage is going into the anode, so we've got a voltmeter there. In the past I have used a moving meter, thing like this. All well and good, but they're not as accurate as a digital multimeter. Again, we need a meter set up to read the current going through the valve, and then we also need to meter obviously what screen grid voltage we've got going in. And another one I haven't shown here is what we also need to know what bias voltage we're feeding the valve. So that is 1, 2, 3, 4 meters in total. If we include a GM meter, then that's 5 meters in total. In the past I have used my Fluke 25 digital multimeters. It seems daft having a bloody couple of really good multimeters there and not using them, but we'll see. I haven't thought about that yet. Right, not shown on this schematic, rough schematic, is things like heater cathode short test and inter electrode short test. I haven't bothered on version 1 of this valve tester. I didn't bother with that, A, because I didn't know how to do it at the time, but B, after using the version 1 tester for quite a few years, I could see pretty much straight away, just from how the valve behaved, whether it had any problems with shorts. And I think I must have tested about getting on for 500 valves, probably more. I think I've only had about a couple that have had a direct into electrode short, be that heater cathode or whatever. But like I say, usually when you've used any bit of test equipment for a while, you get to know how it behaves, and then from how it behaves from your general day-to-day usage, you can intuit a lot of the times how it is reading and what it is doing, whether the device you're testing has a fault or not. Next, I need to start having a think about where everything goes. This is pretty much fixed as it is. These are our, sorry, I got my fag there. These are our test valve bases. Only got 5: B9A, Octal, UX7, UX5 and B7A. And maybe I could put a Loctil on there or something like that, but most of the valves I use are either Octal or B9A or B8A or B8E, whatever. And I found that for what I do, that suffices. However, I'm going to have to put another couple of valve bases down this end if I'm going to use that valve regulated anode supply, so I'll probably put them down there. And then I really need to start thinking about the panel layout and what sort of meters I'm going to use to monitor all the different voltages and currents and all the rest of it. I know you can get these where the bloody hell are they? One moment. I know you can get these cheap Chinese digital meters, however I did fit this to version number 1.2 or whatever and found it wasn't accurate enough. I thought it was pretty crap, but maybe I just got a crap one. But I know on the Sussex, which was a valve tester that was a chap sold it on the forum that I'm on, designed some time back. He used all these sort of things, but then and again I like my old panel meters. They look snazzy, don't they? Even if they're not as accurate probably as a digital multimeter. So I'm going to go and get my thinking cap on, start like scribbling on some bits of paper and all that, and then hopefully in the next video we'll start getting down to some nitty gritty and start actually building something. Thank you all for watching. Take care of yourselves. Ta-da for now.